new thing was the neuroscience center.
Was the
Neuroscience.
yes.
Started on the first of this month.
Right.
So they've been able to track along very quickly.
Right. It's not the same board of directors for them, though, is it?
Yeah. They're part of
I know they are, but do you? I mean, your board of directors is the same as all. Okay, gotcha. Okay, it's the board of directors for all of the centers. Okay. Yeah, at some point you should show me the labs. Yeah.
Oh, yes.
Yeah. Yeah. Anytime, of course, but I'd like to see them before I leave. Hello.
Okay.
Okay, so can you hear me? I think you probably can. Okay, so it's my privilege to introduce Professor Raymond Bishop, who's the research professor of theoretical physics at the University of Manchester. He's one of the world's leading quantum many-body theorists, and very well known for his contributions to the coupled cluster method. And he is the recipient of the Eugene Feinberg Memorial Prize, which is the premier international prize in the field of quantum many-body theory. Professor Bishop has contributed to many areas of quantum many-body theory, nuclear physics, subnuclear physics, condensed matter, as well as quantum information. And we are very fortunate that he'll be giving us a set of lectures, 3 lectures actually. Today is the first lecture. The title is Confronting the Quantum Many-Body Problem, an overview of the coupled cluster method and its applications in physics. So with these few words, I would like to request Professor Bishop to come talk.
Do I need that one or this one? Is the microphone working? Can everyone hear me online as well? Can we get rid of that?
Yes.
That automatically just there. There we go. So thank you, Banu, for your very kind words of introduction. What I would like to do today is to give you the very, very broadest overview of what the coupled cluster method is, how it sits within the framework of quantum many-body theory and quantum field theory, and to give you just the barest flavor of a diverse range of applications. I thought about whether I would tech this or not, and I thought maybe I won't, because this is really in the spirit of not a research lecture, but of a general talk, and I think this gives perhaps a better flavor than to teching everything, which makes it look very polished and very fancy. And that's not what I want to do. What I want to do today is to give you a flavor of the power of the methodology, a wide range of applications. And then in lectures 2 and 3, I shall hone in on the work that we've been doing most recently on spin lattice problems in quantum magnetism. And on the second one, I'll give you a sort of tutorial introduction to the field. And in the third one, we'll delve much more deeply and go into a state-of-the-art calculation. So with that, what I want to do today is to very briefly give you an introduction. What are the many-body systems that we're interested in? What are the available techniques? Then to say why the coupled cluster method sits very near the top of the hierarchy of methods of choice, and then to give you a flavor, a very quick flavor of some of the very diverse set of applications which I have indicated here. And this is just a selection from many more. So suppose we are thinking about many-body systems. So what are the systems that we're talking about? And of course, they cover virtually the whole of physics, certainly of non-classical physics. So if we're dealing, for example, with molecular clusters, carbon dioxide molecules, the interactions, typical van der Waals type, repulsive core, attractive tails, and the infinite limit then is a gas or a fluid or a molecular crystal. And we would ideally like to be able to understand from the interactions as far as possible, how do we go to the macroscopic phases? So as a many-body theorist, I'm typically, not always, but I'm typically interested in going to the infinite lattice, to the infinite system. If we're dealing with rare, oops, no, what did I do there? How do I guess one tap brings it to the next page or something. Okay. If I'm dealing with rare gas atoms, for example, helium, then of course our many-body system is liquid helium, liquid helium-3, liquid helium-4, some of the most challenging many-body systems that we know. If we're dealing with metallic atom clusters, sodium, gold, silver, then we end up with a metallic crystal. Where the method is perhaps most used is in the framework of atomic physics, or at its boundary with quantum chemistry. And there our elementary particles are electrons and nuclei. The interaction is Coulombic, very well known. So we're in a situation where we know the interaction extremely well. These days we would be interested in relativistic effects, QED effects, and typically we would stop at a finite system. But of course, the infinite limit there would be an infinite Thomas Fermi atom. Suppose we turn our attention to nuclei, for example. Let's say a nuclei where we have an equal number of protons and neutrons, just as an example. So we could know what are the fundamental particles. Now it's not so easy. It depends what energy scale we're talking about. At one level, we could say we've got a collection of alpha particles. And the infinite, and there would be a two-body phenomenological potential describing the interaction between alphas. Not fundamentally known. At perhaps a slightly deeper level, we would have nucleons, neutrons and protons. Again, two-body phenomenological potentials. We do not know the potentials. We do not know, or we did not know, whether two-body forces were sufficient, or would we have to go to three-body forces? And I'll come back to that. And the standard and the infinite system there would be standard nuclear matter. Now we can go sort of think of peeling the onion skins off, and underneath the nucleons, we've got mesons as well, and we've also got heavier baryons. And if we peel the onion skins off more, we've got quarks and gluons. So in nuclear physics, we're much more unsure of what we should be doing. And one would like to start and see how well we can do here, and then how far down do we have to progress here. So that's the kind of game. The sort of things that we've been doing, and I will concentrate in much more detail in the lecture on Wednesday and continue on Friday. Suppose we put spins on a regular spatial lattice, hundreds of examples of these things in reality. Again, the interactions tend to be very simple. Spin dot spin, Heisenberg interactions, nearest neighbors, situation where you know the interaction extraordinarily well, but almost no exact solutions for any of these problems, extremely challenging problems. And we'd like to go to the infinite lattice case. And of course, you can go all the way down to elementary particle physics, where even, of course, for the physical vacuum is a many-body problem because it's got a number of virtual excitations of anything that's around, right? Virtual pions, virtual electron-positron pairs. So in some sense, the vacuum is the most complicated of all many-body problems. So we would like to know, what methods do we have for attacking this whole array of problems in principle? And so let me come to that. So as I say, from the perspective of fully microscopic ab initio quantum many-body theory, we'd like to have a formalism powerful enough to treat both in principle and in practice all of those systems that I've just described. So what are the contenders? So I've tried in one sheet to summarize what the main methods, what are the contents of a many-body theorist's toolbox. I don't pretend to describe all possible methods. What I do try to do is to describe methods that have this universality. Of course, there are specialized techniques for particular systems, but I'm interested in at the moment of techniques that have a very wide in principle and in practice. Now, perhaps sitting at the top of these are, let's call them quantum Monte Carlo techniques. They come in a whole variety of flavors: Green's function, diffusion, path integral, Monte Carlo. They're all predicated on essentially the classical Monte Carlo, with typically with this famous metropolis algorithm that was invented, I suppose, just at the very end of the Second World War, when the very first computers, not quantum computers, the very first general purpose computer was on hand. And one of those was at Los Alamos. And people like Johnny Neumann were wondering, what can we do with this machine? And that was how classical Monte Carlo got invented in classical statistical mechanics. And the idea there basically is you put a random walk through your phase space, but you weight him into places where the phase space is denser. You do that, you do essentially the same thing in quantum Monte Carlo, but your probability function is now the wave function, the many-body wave function, not wave function square. You can't do it. You've got the U because you're solving the Schrödinger equation, and the Schrödinger equation is for the wave function, not the square modulus. And that's fine if you're dealing with something like bosons. Bosons in their ground state have a wave function that is of uniform sign. You can describe it to be all positive or all negative, just a phase, right? No, not all positive or all negative. You can describe it to be positive definite is what I mean, up to an arbitrary phase, which is irrelevant in quantum mechanics. There are no nodes in the wave function. So that works as a probability. That means that you can do something like liquid helium to liquid helium-4 to very good accuracy, and you can get benchmark calculations. The moment you go to more complicated systems where the wave function has nodes, like for all fermionic systems, all bets are off because the wave function is no longer positive definite. You have this infamous minus sign problem. And basically, the Green's function Monte Carlo method is not applicable. So it's basically only applicable to a set of measure zero problems. But where you can do it, it provides excellent benchmarks. Now, what else can we do? I mean, think back to undergraduate quantum mechanics. What do you learn in quantum mechanics when you can't, you learn the classic problems, the hydrogen atom, the oscillator, and then you ask, how do I solve a real problem where there's no analytic solution? One thing you do is perturbation theory. In particular, time-independent perturbation theory, and you can do the same in quantum many-body theory. It's much more complicated, of course. You can set it up diagrammatically. You get a set of Goldstone diagrams, an infinite set of them, and somehow you've got to find a method of choosing the ones that are most important. For most interesting problems, you have to do some partial infinite resummations. And you don't really know a priori what to do about that. You can do the same. They're called Green's function methods for time-dependent problems. What else do you do in undergraduate quantum mechanics? Well, you do basically perturbation theory or variational calculations, and you can do the same. You can do the same for many-body theory. Typically, you have a trial wave function. Typically, in many-body theory, it's of Jastrow form or of Jastrow more complicated form, and then various techniques to calculate the expectation values. They're very difficult. Of course, they're many-body integrals. In principle, they're infinite dimensional integrals, and you have to find some method to either analytically resum certain classes. There are things called like the hypernetic chain approximation, or you do a Monte Carlo evaluation. However, even when you've done that, you haven't got the exact answer. You've just got a bound. And in general, you don't even get a bound because you have to make approximations on how you calculate the energy expectation value. So often you even destroy the bound. Question is, can you do better if you start with a variational calculation that you've optimized? Is there now a methodology for systematically improving that? And the answer is yes, there is. It's the method of so-called correlated basis functions. And that was the method that was invented by Eugene Feinberg a long time ago and was then pursued by his students. I'm not going to talk about that method. What I am going to talk about is, and the other thing that you can do is when you're faced with a many-body Hamiltonian, is you can say, I can't diagonalize this Hamiltonian in an infinite space. Let me carve out a finite subspace. And how do I do that? Well, I have somehow to choose what is the most favorable part of the Hilbert space. And of course, that's an art. And then what you do is you diagonalize the Hamiltonian in that finite subspace, and you do bigger and bigger subspaces, and you try to go to the exact limit. That's what's generally called in nuclear physics. That would be the many-body shell model. In most of the rest of physics and chemistry, that's called the configuration interaction method. And the coupled cluster method is typically a way, and this has real problems when you go to infinite systems, as I shall try to describe to you. And the way to try to solve those problems is the coupled cluster method that I'm now going to try to describe to you. Now, there are other things on here that I've left off. There are things like density functional theory. I put question marks here. Watercone, who invented the method, totally agreed with me. There should be question marks here because it is not really systematic. But there are other methods, okay? But the one I'm going to hone in on today is this one. Let's perhaps just come back one. So the deal now is that what we were trying to do is to look at methods that have the potential to deal with this wide diversity of systems And one of the take-home message, first take-home message today is there are really probably only two contenders that satisfy all of my criteria. You want it to be fully microscopic. I don't want to make unnecessary approximations or do a particular theory for a particular system. I'd like it to be widely applicable. Very importantly, I'd like it to be open to systematic improvement. I don't want a one-shot, like a variational calculation is a one-shot. You would like to know how to systematically improve. So we would like to have hierarchies of approximations, and I go as far as I can, but I know if I go as many steps as possible, I'm going to get the exact result. And then as many steps as I have got computer power is what I typically would do. And I'd like it to be very accurate in practice. I'd like it to be widely and deeply tested. And really, there are only two contenders: the coupled cluster method and the correlated basis function method. I'm going to talk wholly about the former. I should say, if anyone has any questions, I'm very happy to be interrupted as we go along. So let's come and say, what are the elements of this technique? So as a start, let's suppose that I'm dealing with a closed shell atom or a closed shell nucleus. Let's take a nucleus just for.
Professor Bishop, I have a question.
Yes.
Yeah, this is Vijay Sahu.
Hello.
So, is it possible to show the relation between coupled cluster theory and correlated basis function method?
They are very, very different from the starting point, but there have been some very deep. There is some very deep relationships between the two, which have been studied. But it takes me outside the realm of what I've got time enough to talk today. But the answer to your question is yes, there have been studies, and there's some very interesting relationships between the two.
Okay, thank you.
So suppose we are dealing with, let's say, calcium-40, a nice closed shell nucleus, 20 neutrons, 20 protons. How are we going to describe it? Well, the starting point, and there's always got to be some starting point. If you use the word correlation anywhere, you're talking about correlation with respect to something. Okay. Typically, when you would ask, well, what's the simplest possible thing I can do? The simplest possible thing I can do for a closed shell a nucleus like calcium-40 is to come up with a set of single particle orbitals, and they could either be from a square well, from a harmonic oscillator well, or perhaps even better, from a self-consistent Hartree-Fock well. And we will talk about all of these. I've got a set of orbitals. I filled them up. I put the 40 particles in satisfying the Pauli principle, and there's a top level, the Fermi level. So that's my uncorrelated state. It's a single particle shell model state. It's a Slater determinant, right? So it's just a physical vacuum. I take in second quantized language. I create all of the particles in these lowest 40 states. I say this is an arbitrary basis. Now, if you don't like my basis and you have another basis, if you don't like harmonic oscillators, you do want Hartree-Fock, it doesn't really matter, because there is a general theorem due to David Thouless that says an arbitrary Slater determinant can be written in terms of another arbitrary Slater determinant by an exponentiated one-body operator. And that one-body operator is a one-particle, one-hole operator. It just excites one of these particles from below the Fermi sea to something above the Fermi sea. So that means that now, this of course is not the exact eigenstate of any interacting Hamiltonian. It's certainly not the ground state of the of the nucleus with whatever potential I put on. But what can I do? So I've now got to describe other parts of the wave function. Now, the first thing that you can do is to say, well, there's another component of the wave function, which I will call a single pair excitation, two particle, two hole, where I simply excite two particles from below the Fermi sea to above the Fermi sea. And that's a picture of one of those. Okay, I can describe it with a two-body operator. For the moment, I'll put hats on operators, and then sooner or later, I'm going to forget to put hats on. So this is an operator, and what it does is it destroys two particles in these states, and it creates them in these states. And the language I'm going to use is the labels nu are labels below the Fermi sea, so those holes, and the labels rho are above the Fermi sea. That's, of course, not the end of the story. The next thing I can do, having been able to do that once, I can do it twice, right? So this is the same thing happening twice. That's obviously described by just S2 acting twice, S2 squared. Now, really importantly, there's also a factor of a half, and that's got nothing to do with quantum mechanics. That says I've got to properly combine, I've got to properly count these things, and these are after all identical things, and so there's a half factor. In general, if there are n of them, there's a 1 upon n factorial. That's just standard counting of independent things. So that's not the end of the story. Obviously, there are triplet excitations, and that's an operator S3. Now I continue. Add up all of the independent pairs. That very important counting factor, nothing to do with quantum mechanics, just to do with combinatorics, add those all up and I get an exponentiated operator. That is the second take-home message. That is the heart, the very first heart of the coupled cluster method, is the importance of exponentiating operators. If I left that operator linear and still expanded it in one particle hole pieces, two particle two hole pieces, etc., that would be the configuration interaction method. We're replacing that by an operator F linearly. And we'll see why that's not the best thing to do. Then I add in triplets, and I get this. Now, notice, I have no problem with Baker-Campbell-Hausdorff because S2 and S3 commute. Why do they commute? In physics terms, they commute because they've got nothing to do with each other. These are independent things. Triples and pairs are independent. Mathematically, they commute because every one of these guys, all of the undaggered operators have labels below the Fermi level, and all of the daggered operators have labels above. And therefore, there's no way that any piece of one of these operators can commute with another piece by construction. That's a second take-home message. We are automatically counting independent things. And commutation of these guys is what comes in and does that. Okay, pause. Is that clear? They commute because, I say it again, first, they must commute because they're different things. Mathematically, the way they commute is because why would they not commute? The only place the second quantized operators don't commute is when one of the terms meets its Hermitian counterpart. That right? It's A and A commute, A dagger and A dagger commute, all of A's and all AI, AJ commute. The same for the daggered operators. It's only when you have AI dagger commutator that you get something that non-vanishing. And these guys, they can't, these labels can never meet their Hermitian counterparts because the Hermitian guys are always different labels. Is it clear? It's a very important point that is clear. Okay. Now, very quickly, I'm not going to concentrate very much on this. Suppose I have an open shell system, and this is what you would have in quantum chemistry or in nuclear physics. Instead of calcium-40, now let's add one valence particle or one valence hole. Now, this is then called multi-reference coupled cluster method. And basically what you do is you say for the n+1 particle particle problem, I'm going to keep my exponentiated guy here. So that's the core. On top of that, I'm going to create one extra particle. That's the extra valence particle or the extra valence hole. There's some C number coefficient which does that, and then there's a new operator which comes in, which describes the interactions of the valence particle with the core particles. All of the core particles, I've done a lot of work, so I keep all of that work for the core, and so I add another. Then you go on and you can do this for 2 valence particles. I'm not going to describe that. I really don't have to, because it's not going to be interesting for my infinite problems. But it's very, very interesting, and it's vital for quantum chemistry. But you have your own homegrown experts here. In particular, one of the several of the founders of multi-reference. One of them is Debashis Mukherjee. So if you want to know about multi-reference coupled cluster method, you ask Deb. Now, so that's how you do it with for something like a closed shell nucleus. How would we do it for other systems? Because I started out by saying I want a formalism that works for all many-body systems, or as many as I can possibly conceive. Now, what are the keys? The keys that I need to put the CCM into effect. I always need what I will call a model or a reference state. Now, in mathematical terms, this guy is what's called, for mathematicians, would call a cyclic vector. What that means is, with respect to that state, I can define 2 abelian subalgebras. Abelian just means mutually commuting in this sense. And I'm calling these creation operators. This index I is a set index. For example, for the calcium-40 nucleus, this was a 1 particle 1 hole, 2 particle 2 hole, 3 particle 3 hole, etc. But if I count all of them, I know in principle, if I cover all possible for the calcium-40 nucleus all the way up to 20 particle 20 hole, I would have an exact description of the wave function. Right, so this is a complete set, and very importantly, on top of that guy, I've got these guys, and these guys all mutually commute. That's the abelian subalgebra, if you like mathematics rather than physics. Their Hermitian counterparts are called the destruction operators, and the bra state can be similarly expressed in terms of these guys. Okay. So all I need is for the CCM to work, is I need to be able to choose a phi, choose a set of operators, all of which commute, which span the entire Hilbert space. And that's it. The moment you've done that, the CCM apparatus can be put into effect. Hopefully that's clear from what I've said already. If it isn't, again, just shout. So it's very convenient. We don't have to, but it's very convenient if I orthonormalize these states. Often they're orthonormal already, but if they're not, you just do a Gram-Schmidt orthogonalization on them. They're complete by construction. They're complete. And if you like, I'm not going to go into this. You can have a Wick's theorem for these. There can always be a Wick's theorem proven, which is very useful if you're doing diagrammatics. Now, examples. Well, the one I just mentioned, number-conserving Fermi systems. Phi is a slated determinant. These guys are products of particle hole pair creation operators. By construction, commute. Interestingly, a BCS state is also a perfectly valid starting point, because a BCS is just built out of renormalized particles, which are a linear combination of particle and whole. So that works too. Number conserving Bose system. Well, the thing that plays the role of the Slater determinant for bosons is the zero momentum condensate. And so then the CI daggers are just products of, again, particle wholes, but the particle is just something that's, the whole is just something that's left in the zero momentum condensate by construction. It's Q equals 0, and you promote it up to a higher value. Number non-conserving bosons, field theoretic bosons, you can take phi as the bare vacuum. And then the creation operators are just products of single boson creation operators. And for the quantum, the spin lattice problems that I'm going to be dealing with, for example, suppose we have an antiferromagnet, a really classic antiferromagnet, Néel state, all nearest neighbors have opposite spin. So spin up, spin down, alternating across, let's say, a checkerboard in 2 dimensions, or on a hypercubic lattice. Then that is also a perfectly valid starting reference state, because how do I get all of the other components? Well, I start with whatever these are, and I start flipping the spins to, let's say, from right to wrong positions. And again, by construction, these guys are going to commute. So you see, there's a very general framework and a very general and a whole set of possibilities. So now, how does the method work in practice? So a bit of it's not even mathematics, but let's call it mathematics. So my ket ground state, I put a 0 on for the ground state. I'll come to excited states later. We can also deal with excited states. So let's just stick with the ground state first. This exponentiated operator. So I've dropped the hats now, but hopefully that should be understood. And this S is a combination of these multi-configuration or creation operators. So whatever the problem is at hand, but by this compact notation, I can describe any system. Okay. Notice by construction, this guy is not normalized to itself, but it is normalized to the model state. That's easy to see, because if I sandwich e to the s between phi on the right and phi on the left, expand out the exponential, it's 1 plus something. The 1 gives me 1, and everything else gives me 0, because the S operator, when it acts to the right, gives me something, but when it acts to the left, it destroys it. Right? This phi is a generalized vacuum state. So all of the bits of S, when they act to the left, give me 0. How will I find the ground state energy? Well, I plug into the ground state Schrödinger equation, plug this in, pre-multiply by e to the minus s, and I get this equation. So this is a similarity transformation of the Hamiltonian as popped up here. Okay, is that our third takeaway? I'm not sure. Next takeaway, similarity transforms of the Hamiltonian are what come up in the coupled cluster method. So this is my Schrödinger equation written, many-body Schrödinger equation written in the CCM form. Now, I'd like to calculate the energy, and I'd like to calculate all of the bits. If I know these coefficients, I know everything there is to know about the ground state. Right? How will I find them? Well, first let's project with phi, and obviously projecting with phi on the left itself gives me this equation, because the E0 piece, phi is not, by definition, phi is normalized to itself. So if I know all of the bits of S, I've got the energy. So how will I calculate the bits of S? How will I calculate these? Well, what I'm going to do is I'm going to project onto This is, and I have as many of these equations as I have unknowns, right? Now, be careful. There's no general theorem now that says n linear equations in n unknowns have a unique solution. These are not linear equations. So all bets are off about how many solutions. Are there any solutions? Give this to your mathematician friend and they throw their hands up in horror and they say, how in God's name, Ray, do you know these equations are robust? How do you know? And I say, well, I do know because this is physics. This is physics with proper counting. It's got to work. You know, that's the arrogance, if you like, of a physicist over a mathematician. To me, it's not arrogance. It's knowing where an equation comes from, right? And mathematicians will acknowledge that. If you know where an equation comes from, rather than just writing it down out of the blue. Now, this is a set of n coupled nonlinear equations because of this guy. Now, I'm going to tell you that this way of writing the exponential automatically incorporates what's called the Goldstone-Link cluster theorem. Now, those of you that know that those words will appreciate it. Those that don't, I will tell you what it really means. If you calculate an expression like this, but where this e to the s operator has been replaced by a linear operator, which is what you do in configuration interaction, what you find is when you expand out, you've got terms, when you do the expansion, some of which scale like n, which is what you want. Energy is usually an extensive variable, but there are bits that scale like n squared and n cubed and n to the fourth. And when you want to take the limit of n goes to infinity, you are in deep, deep trouble. This solves that problem, and I can show you how it solves that problem. In diagrammatic terms, if you're familiar with diagrammatic perturbation theory, quantum many-body theory, the terms that scale like n are so-called linked diagrams. You pick them up and they don't fall apart. Unlinked terms, if they have two separate pieces, so when you pick them up, they fall into two, scale like n squared. Bits with 3 scale like n cubed. And when you do a configuration interaction calculation at a finite order, you do get these unlinked terms. And you have to have a way of, in the infinite limit, they go away. They're there, but they sum to 0. But when you make an approximation, they don't sum to 0. So you've got to be really, really, and this solves that. It's easy to see. By the way, this exponentiation might be familiar to you in classical theory as well. I said this, the 1 upon n factorial, which is what led to the exponential, is not unique to quantum mechanics. That occurs in classical mechanics as well. In particular, it occurs in classical statistical mechanics. And in classical statistical mechanics, you have a cluster. You also have a cluster expansion, typically of the sum over states, and that's called the Ursul-Meyer cluster expansion. And at its heart, it's got an exponential as well. This is the sort of quantum analog of the Ursul-Meyer cluster expansion of statistical mechanics. Now, the nice thing about this similarity transform is that it has an expansion, the nested commutator expansion. Be honest, is anybody not seen that expansion? Be honest, because I'll tell you how to prove it if you don't know it. It's dead simple to prove. Instead of S, put lambda S and make a Taylor expansion. You immediately, within 2 lines of algebra, you arrive at this. Okay, it's just a Taylor expansion of if you change S to lambda S. But it's infinite. So you think, oh, hell, I'm going to have to make an approximation to chop this somewhere. Not true. 4th takeaway, is it 4 or 5 now? Next takeaway lesson, this terminates exactly for almost every problem at hand. Why? Now, the deal goes as follows. The Hamiltonian is comprised in second quantized form. It's just strings of A dagger and A operators, sums of products of them, right? If it's a one-body potential, kinetic energy, A dagger A terms. If it's a two-body potential, A dagger A terms. Let's say we've got a one and two body potential. That's what we have in quantum chemistry, kinetic energies and Coulomb. Now, what happens when I do this first commutator? Well, the only place I get non-zero is when one of the terms in S, one of the single particle A dagger or A guys, meets its Hermitian counterpart in, oh, not quite sure how we click to go back a page, but sorry about that. Meets its Hermitian counterpart in H, right? So there are a whole, and of course there will be a large number of such terms, but what I know is when I've done this first step, there's one less operator in H than when I started with. So if I started with a two-body potential that had 4, after this I'm down to 3. Now I do the second commutator. Now here's the key thing. All that can happen now is one of the operators in this guy meets one of the operators in this guy. Now, this guy can never link back to S. They all mutually commute. So the only place this guy can meet his Hermitian counterpart is in H. These are what's called linked terms. That is a linked term. It means that every bit hooks back to the Hamiltonian. The moment I've done that, might be horrible to evaluate, but I do know that now there's only 2 guys left. Do it another time, full stop. It stops at the 4th order term for 2-body potentials. You say, okay, I've got 3-body potentials. I don't care, stops at the 6th order. So no approximation up till now, and that's really, really important. By comparison, suppose I had done, instead of calculating the energy this way, suppose I had done it by projecting onto the bra state, which would be e to the S dagger, and instead of this, I would have e to the S dagger H e to the S. There is no such simple, guys. The full horror of the Baker-Campbell-Hausdorff expansion. You don't know the nth order term. And furthermore, even if you do, and even if you start with a one-body piece of S, it never terminates. It simply never terminates. And that's what happens in variational calculations. And you have to stop. And that's why, in practice, you break the variational bound, unless you do it through a Monte Carlo. You can be as exact as possible. But if you have to do something analytically or quasi-analytically, this so-called unitary rather than similarity transform is much, much more complicated. Okay. That is the proof, actually, of the Goldstone link cluster theorem. You can never get unlinked terms. And once you've not got linked terms, the energy is going to scale, even when I truncate this S operator, which is what I'm going to have to do in practice. Even when you make truncations, you are guaranteed that the energy will be an extensive variable. Furthermore, I can start in the infinite. I do not have to start with a finite problem. If I'm interested in the infinite limit, I start from the outset with the infinite system. And that also is very unlike almost all competing methods. Okay, very quickly, what would we do for the bra state? I don't like e to the S dagger. I do like e to the minus S. E to the minus S is not the same as S dagger. So to correct it, I will put another operator in front of it, which makes it exact. And I call that other operator S tilde. And S tilde has got a one-body piece, and then it's got these multi-configurational destruction pieces because it's acting that way. It breaks hermiticity. When most people see that for the first time, they think, oh, that's pretty bad. Let me tell you, it isn't so bad. You have two choices in physics, in many-body physics, which most people do not realize. You can preserve hermiticity of the Bra and Ket states, or you can preserve the Hellman-Feynman theorem. The Hellman-Feynman theorem says in layman's terms that if you want to calculate the expectation value of another operator that's not the Hamiltonian, you would like to keep, for consistency purposes, exactly the same set of diagrams or exactly the same underlying approximation. That's the essence of the Hellman-Feynman theorem. Can you do both? Can you do hermiticity? Can you satisfy hermiticity and satisfy the Hellman-Feynman theorem? Yeah, but there's only one theory that does that, and that's the exact theory. Any approximation you make breaks one or the other. You cannot hold both. CCM chooses to preserve the Hellman-Feynman theorem, and in practice, it's vastly more important. Furthermore, if you can always check at the end of the day, at any level, you can check how unhermitian your problem is, if you wish to do so. In practice, the lack of hermiticity, except at the very lowest orders, is almost insignificant. Okay. That then says I can go to an arbitrary expectation value, and I need both of these sets of coefficients now, right? For the Hamiltonian, because I have the Schrödinger equation, I didn't need these guys. Well, how will I solve for these guys? Well, either by, I mean, what we did for these guys was plug into the Bra state Schrödinger equation. Equivalently, you can plug into the ground state, the Ket state. No, Bra state. For these guys, we use the Ket state. For these guys, we use the Bra state Schrödinger equation. Completely equivalently, you've got the static variational principle that says the Schrödinger equations for the Bra and the Ket state are fully equivalent to extremizing the expectation value of the Hamiltonian. Extremize with respect to the S tilde operators, they only came in linearly, right, in front of this. So when I set this partial, why is it doing that? Whoops. There we go. There we go. Right, remember where the S tilde coefficients appeared in front of this, vary with respect to them, and we simply get the equations that I had before. Now, what about for the S tilde guys? Well, now we extremize with respect to these guys. Now, this appears twice, right? They appear both in this exponent and this exponent, and if you just vary with respect to the guys sitting in the exponent, you just pull down this commutator. But this is a linear set of equations because this guy appears linearly. So these are the equations for a given index I. This is the equation that determines the S tilde I coefficient. This is an easier set of equations. This is a linear set of generalized eigenvalue equations. So that's how you solve everything. The moment you've got these S's and S tildes, you can calculate anything for the ground state. Very quickly, I'll run over it because I'll come back to this in future lectures. You can do dynamics in exactly the same way. Instead of, Dirac told us what to do for dynamics. Instead of minimizing the energy expectation value, we minimize the action. And this gives us a set of equations for the time-dependent coefficients. I'll run over this very fast because, as I say, I will come back to that. If you're interested in excited states, you've worked very hard to correlate the ground state. You've worked very hard to get this exponential. Just put another operator, and a linear operator is enough. It turns out this time you don't generate any further unlinked terms, and you do exactly the same machinery. Exactly the same machinery. And all that happens at the end, obviously, if I keep all of these coefficients, it's exact because I've made no approximations up to now. So the only thing I have to do now is decide which of these multi-configurational set of configurations will I keep. Now, for example, if you are doing quantum chemistry, you typically do what is called the sub-n, and it says I will keep 1 particle 1 hole, 2 particle 2 hole, 3 particle 3 hole, all the way up to little n particle n hole. In practice, so that's doing another way of saying the same thing. At the level of sub-2, you include both single excitations and double excitations. And the usual language of quantum chemistry is that's called CCSD, coupled cluster, singles, doubles. If you want to go further, you do CCSDT, singles, doubles, triples. Everyone does doubles. It's already an extremely accurate approximation in quantum chemistry. If you really want to push the boat and get the best you can do by any method, you do triples. It's a very expensive calculation, and mostly it's done with including triples perturbatively, but that's the gold standard now in quantum chemistry. In other fields, you do different approximations, and what you do in quantum magnetism is different to this, and I will just, because we're on a lattice, and I will tell you that on Wednesday. Let's skip this and ask, what does the sub-2 approximation? So this is, I'm now looking at an infinite system. For an infinite system, the nice thing about infinite systems is the one-body piece is 0. Automatically, identically 0. Why? Because if you start from a field Fermi C, let's say we start with plane waves, and you've got to start with plane waves because you've got translational invariance for an infinite system. So translational invariance tells you what your single particle states are, and they're plane waves. So the Fermi level now is you fill up the states with the states now carry a label of the momentum. You fill up to a KF, Fermi momentum, and then it's free above. Now, of course, if you try to excite a particle with a momentum less than KF to something with a momentum bigger than KF, and you want to get 0, you can't, right? The momentum is not conserved. So the nice thing about infinite systems, which you are faced with for finite systems, is where you work so bloody hard in quantum chemistry to get the best possible Hartree-Fock wave functions. In infinite systems, you know what they are, they're plane waves. And it doesn't matter as long as you've got a translationally invariant system. Okay. So the lowest approximation is doubles. Now, if you now try to do a diagrammatic expansion of this second order nonlinear equation, it looks like this. Now, what's this E0? This E0 comes from, remember, H is T plus V, kinetic energy plus potential energy. The H0 is the kinetic energy. Oh, damn. Got to learn to keep my fingers out of the pie here. So the kinetic energy piece, or the one-body piece, let's say, has got eigenstates, very trivial eigenstates, which for the infinite system are just plane waves. And so this would just be a p squared upon 2m, single particle basis. And the E0, when it acts on an S2, is what comes from working out that one-body piece. No great surprise, it's the sum of the particle energies minus the sum of the hole energies. That's the excitation energy of a two-particle, two-hole excitation. So what you've got is that you start out with an equation which is E0 acting on S2 plus a whole load of terms that come from V equals 0. You can rewrite that that S2 is equal to -1 upon E0 times all of the terms that come from V. And that's what I've done here. Pre-multiplying e to the S2, E0 times S2, there's a minus sign, plus all of that lot that come from V is equal to 0. That's the Schrödinger equation at the two-body level. So you rewrite it like this. So there's a leading term, which is just V. And this is how I'm describing V. This dashed line is a V, and it's got a particle hole pair. So it's a two-particle, two-hole piece that comes from V. Now there's a whole load of other terms. This is the, let's say, the Hartree term. This is the Fock term. Because statistics are properly built in here for fermions. So we've got these two pieces, and then we've got a whole load of terms that come from S2, and some that come from S2 squared. Now I've lumped them together in a way that I hope makes sense. Suppose I just stop at the first line and ignore all of the rest. Now, the nice way of writing it like this is, I never do in coupled cluster, but I can make contact with perturbation theory, and this is the way to make contact with perturbation theory. I do assure you, I am not going to solve by perturbation theory, but I can make contact. How do I do that? Well, I just iterate this equation, right? So that's what I do at 0th order. At next order, I replace S2 by a V. And then you keep iterating. And I think you will rapidly see, if you do this, you will generate all of these terms that have rings or bubbles in them. This is the so-called ring approximation. You include all of the rings, and this is what's generally called the random phase approximation. This was invented for the electron gas a long time ago in the 1950s by David Bohm and David Pines. If you do the electron gas and you try to do perturbation theory on the Coulomb potential, after second order, all of the terms are infinite. Bohm and Pines said, I mean, it's a bold step. What we've got to do is select all of the most divergent terms and sum them together, and they will be finite. It's a bold step, but it was true. And this is the set of terms that is finite. It's called the random phase approximation. It works for the very high density electron gas. It's exact, but it's not the end of the story. There's a whole load of other terms. This is I call this, how do I get rid of that? Touch it, slide it. Very good. So that's the random phase approximation. Oh no, I've done it again. Okay. Learn. There we go. Random phase approximation. Random phase approximation exchange terms. Obviously, just comes in from fermion statistics. There's another set of terms. I call this the complete Hall potential. It's kind of obvious, isn't it? This is an insertion on a Hall line. This is a Hartree Hall potential. This is a Fock Hall potential, and this is a self-consistent Hall potential because it's built out of S2 itself. So these are Hall potential corrections. This is the same thing on particle lines, complete particle potential. Suppose I just forget all of the other terms and just take this line, of course, including the V that I started with, and iterate on this. So if I replace this S2 by a V, I've now got the thing that looked exactly the same as V, but it's got two rungs on the ladder between particles. This guy has got two rungs on the ladder between holes. And this guy has got all possible ladder diagrams. The guy that includes all of ladder diagrams is what the starting point is in nuclear physics, the random bubble diagrams for electronic physics, and this is called the complete ladder sum. This is synonymous with Bruckner theory. And then there's other terms. This leading approximation in in the CCM is already unbelievably rich. It contains virtually every other approximation that was known before it, or in fact many that were since. And it's the lowest order. So this is coupled cluster singles doubles. Incredibly rich. One, the ladders work for systems at high density, the rings at high density, the ladders for low density. So you got somehow both are included. They're not only included, they're included self-consistently. It's not just rings and ladders, it's rings of ladders of ladders of rings and right? It's all of those self-consistently put together, which nobody had ever done before this, because nobody tried, but it's very easy to overcount or undercount. This will never improperly count because we started with proper counting. And that was that one simple step of exponentiating, and it's led to this. So you start very simply. Of course, when you do the algebra, normally when I have a student coming to do coupled cluster theory, I say, derive this as, for yourself. It takes the average graduate student about 2 months to derive this equation. And if they're good, it's not trivial. There's a lot of algebra. These days, we don't do it by hand. We teach our computers how to do algebra, right? How much time do I have, Manu? Much? Any? Okay, so let's just get a flavor of the sort of things that we can do. So some of the my fingers are evidently much too fat. I'm going to skip this. So this is coming back to the sort of, just to flash again, the sort of things we can do. Let me just give you a very quick flash of, let's say some of the results in nuclear physics. So here's let me just come back to here. So the things we're interested in nuclear physics are finite nuclei, closed shell, open shell, 1 or 2 valence particles, and infinite nuclear matter. Now, a long time ago, Hunts-Bethe posed the question, can we, with 2 body forces alone, accurately describe the properties of the known nuclei, and at least the lightest ones, and nuclear matter? Now, the state of the art, and this was done quite some time ago, in the late 70s, when computers were extraordinarily primitive in comparison with what they are today. But the power of the method was such that calculations could be done with 2-body and 3-body forces for a wide variety of such systems. And I'll just give you, because we're not really interested in the details, but the coupled cluster method gave a definite answer to Hunts-Bethe's question. Can 2-body forces describe the ground state properties and low-lying excited states of atomic nuclei? And the answer is a definitive no. There is no doubt whatsoever. The answer is no, even though we do not fully know what the 2-body force is. There's a whole range of 2-body forces out there on the market. So it was always possible to say, well, you've chosen the wrong force, or you haven't made your theory convergent. So I'll give you a flavor. This is the oxygen-16 nucleus. These crosses that run from right to left, they are done for 3 different nucleon-nucleon 2-body potentials. SSC is called the super soft core potential. The Hamada-Johnston is a very hard core potential. And the Reed soft core is something in the middle that was at the time believed to be probably the most accurate potential. Now, what I'm showing you in these three curves, this is what you get for those three potentials at the level of just including S2. So you get this line. Now, and it doesn't go through experiment. You say, okay, you've probably done a pretty accurate range of potentials, and they more or less fall on a straight line. And if you do lots more, they do fall on an almost straight line. It's called the Custer line. But maybe you haven't gone far enough. So, okay, we're coupled cluster, we'll include three body. And you get that next curve. And then you say, well, there's a bit of a gap between those two. Maybe three is not enough. So let's do four. Well, is anyone really seriously going to believe if you go beyond, you're not there? Well, you are there, and you don't go through experiment. So the answer is no. Two body forces will not be enough for this nucleus. You've got to include three body forces. And at the time, that was sad for nuclear physics, because not only did they not really know the two-body force, but for sure they didn't know the three-body force. So nuclear physics is complicated, much more complicated than quantum chemistry. Quantum chemistry, we know it's Coulomb, not here. Okay, let's forget those. These are finite nuclei. I don't think you, again, you know it's here. You can do the same for nuclear matter. This is nuclear matter. S2 approximation, S3 and S4, and S3 and S4 now sit really almost on top of each other, and they don't go through experiment. How about the electron gas? The electron gas, of course, is particularly interesting for quantum chemistry. The electron gas is just electrons, one component Coulomb plasma, but you embed it in a neutral background so of charge of the opposite sign, so the system is overall neutral. Okay, you put any electrons in a box, volume omega, let both go to infinity, but keep the density finite. Okay, so what you would like to know is, what is the equation of state? What's the ground state equation of state? What's the energy as a function of the density for this electron gas? Some people call it jellium. It's a nice system to study because it contains only one dimensionless coupling constant. The Coulomb the Coulomb potential doesn't have a range, so there's no length scale, and there's only two length scales in the problem. One is the one range, the one length that the Coulomb has is the Bohr radius. Right, so that's the one dimension that the length, and the only other length is the average interparticle spacing. So just define the volume to be n times 4 pi upon 3 times this guy cubed. So R0 is the average interparticle spacing. So the only dimensionless constant is the ratio of these two things. So the high density limit, is when this guy becomes small, and the other way around. So the RS goes to 0 is the weak coupling limit to the low density, and the other way around. Okay. Now the system is very non-trivial for all values of RS due to the Coulomb potential. So in perturbative terms, you've got to include at least that infinite set of bubble diagrams that I said was included in sub 2, and those are exact in the limit that RS goes to 0. Goes to 0. Now, very unusually, this problem can be solved by Green's function Monte Carlo. Most fermionic problems cannot, because of the minus sign problem. Sepperly and Order found a clever way to get around that, but it was very, very special for the Coulomb case. So there are Green's function Monte Carlo results. Historically, Dave Sepperly and Bernie Alder were doing these calculations at the Lawrence lab in Livermore at the same time when I was at the Lawrence lab in Berkeley, and we agreed that we would not show each other our results until we both had them. The key message here is now the RS goes to zero limit, which is the RPA limit, is we know it's going to be exact. But the much more interesting limit is in the range when this guy is neither big nor small, but it's typically of the order of 1 to 6. Why 1 to 6? Because if you plug in the values for metals, these are the values you get. Real metals have RSs in that range. And of course, that's the worst possible range. It's neither big nor small. So you've got to do, you've got to do one of these really honest calculations where you include high density and low density effects. Well, that's what we did. So this is RS reading across, very small, where RPA should be becoming exact, and out to an RS of 20. And real metals kind of sit in this range of 1 to 6. Now, what we're showing here is the top green numbers are the random phase approximation. The purple numbers are the Green's function Monte Carlo, which took an immense amount of computing power at the time. I mean, this was done 1980, and I guess the biggest computers at the time were at the bomb labs. So that was at Lawrence Livermore. They had the biggest computer in the world, and it took all of that for weeks to get these numbers. It was a real coup. So we can regard these as exact. You have to be careful. They didn't come up with an error at the time. The last digit is not necessarily the one that is still accurate, but it was generally believed that it probably was. But there was not a really good error analysis. These ones down here, this Fermi hypernetic chain was something that came from the best possible variational calculation at the time. But this is coupled cluster. So RS of 1, this is in millirydbergs, right? And a millirydberg is half a millihartree, right? Quantum chemists usually deal with hartrees, physicists usually deal with Rydbergs. How does it go? A hartree is E squared upon the Bohr radius, and a Rydberg is E squared upon 2 times the Bohr radius. The holy grail of quantum chemistry is to get correlation energies. These are correlation energies. This is what you've got left after the Hartree Fock. So I've already subtracted off the Hartree Fock. So this is the tough bit, right? Quantum chemists, the holy grail for quantum chemistry, so this is where cooking occurs, is at the level you want to do at least, you want to get better than 1 millihartree per particle. If you can, you're really as good as you want to be. And what you see by comparing these two lines is we are definitely within 1 millirydberg per particle over the entire density range. So already this shows you that the power of the method on what is probably, maybe was then and probably still is, the most well-studied of all quantum many-body problems. Do I have time for one last example? And I'll make this fast. How about something really simple? How about, let's do field theory, but let's walk before we can run. Let's do, instead of doing a field theory in d dimensions and 1 time dimension, so d plus 1. So if we wanted to do QCD, we would like to do it in 3 plus 1, right? Let's walk before we can run. Let's do 0 plus 1. 0 plus 1 just really means, so it's only a single mode, it's one-body quantum mechanics. But let's suppose we do, there's the harmonic oscillator. Suppose we put a quartic anharmonicity on it. Very easy. There's only one A and A dagger now in our theory. It's convenient. You can, if just to set yourself up the best, you can make a Bogoliubov transformation on these, the same as you would do to do BCS. And you can optimize with respect to these two parameters. And then you're still starting with a harmonic oscillator, but you're starting with a squeezed harmonic oscillator. So that's what we're going to do. And then we're just going to build up. A sub-2 approximation is just saying, well, I'm going to allow 2 excitations, sub-4, 4 excitations, which means one of these guys acting 4 times. Now, you say, well, this is pretty simple. Yeah, it is. But as a field theory, it's very tough because this is just about as non-local as it gets. So it is a severe test. And what we find is already at the sub-2 level, which is the very lowest level now, we're accurate to about 2% for the ground state energy for all values of lambda. Now, let me just convince you, this is not as, this is not as trivial as it may sound. Suppose we were to do perturbation theory. Let's just do plain perturbation theory on this, okay? Just as you're taught, exactly as you're taught in Rayleigh Schrödinger perturbation theory as you're taught in undergraduate quantum mechanics. First order, second order, fourth order, sixth order, eighth order, 10th order. Easy to write a simple quantum algebra program that does nth order perturbation theory for you. So that's all I've done here. I've stopped at rather a small value of lambda. It's only 0.1, and out here I've done it to about 0.02, and it looks all right, okay? Look, you're getting better. What's plotted here is accuracy. Accuracy is the number of significant figures, okay? So by the time you've done 10th order perturbation theory, you've got 7 significant figures at this particular value of lambda. It's getting worse as lambda goes on, but it looks as if it's still okay. Well, it isn't okay, because if I uncover the rest of this, which is the next transparency, that's what happens. And by the time you've got to 0.1, second order is better than first, but every other one is worse. This is a reflection of the fact that this perturbation expansion has a radius of convergence equal to 0. It never converges for any value of lambda, and it's tough. This is a tough problem, okay? And even here, we're pretty small. I'd like to go to a lambda of 1,000. Well, good luck with perturbation theory, right? So you've got to do something. Now, people have tried many, many things. You know, this is only one-body quantum mechanics after all. But coupled cluster done at this level actually is already better than anything that had come before. And let me, now I think I really do have to blow this up a bit. What I'm showing you here, not only do we do ground state, but first, second, third, and fourth excited states. Of course, as you go up in the spectrum, it gets even worse with perturbation theory. These are different values of lambda, 0.1, 1, 10. First row is exact, and this is sub-2, sub-4, sub-6, etc. Okay. 0.1, which was already terrible for perturbation theory, here's exact. That you just do by just an exact diagonalization in a big space, like you can do for a one-body problem. And what you see is, as you go up, this is converging. By the time you've got to sub-8, which is a trivial calculation here, fully converged. Fully converged even for the first excited, second excited, third excited, fourth excited. Again, you're converged to the fifth significant figure. Pretty accurate. And the same is true even at a value of 1. Okay, There's loads more I could show you, loads more different examples. Let me stop, invite questions, and what I will do on Wednesday is to repeat some of the stuff for the coupled cluster method. Now hone in on the particular case of an infinite lattice of spins, and show you, on Wednesday is going to be a tutorial example. I'll take a simple prototype of a spin lattice problem, one that actually can be solved exactly. There's almost none that can be solved exactly, but this is one that can be solved exactly, against which we can compare. And then on Friday, I'll continue in the same vein and show you kind of what state of the art is on systems of real current research interest. So perhaps let me stop there.
The correlation energy you have shown in the last
For the
figure.
electron gas?
Yes.
This
Yeah,
one.
This one, yes.
Yes.
You are telling about the Monte Carlo and your coupled cluster 4. The order of decimal is the first order. This is this much accuracy you are can
So
constant.
this guy
Yes,
is
yes.
what it does. CC parentheses 4. This is not sub 4. It's not CCSDTQ.
Okay.
That would be too difficult. But what we've done here is there's another thing you can do, which quantum chemists almost never do, but I believe should, which is you take the two-body equation and you don't throw away the 3 and 4 body terms. You leave them. So that equation, if you knew S3, and what happens with the equations, the two-body equation, the equation for S2 is coupled to S3 and S4. The equation for S3 is coupled to S4 and S5. And what you typically do in this sub n sequence is at sub 2, you put S3 and S4 equal to 0. Now, in fact, that's a really brutal approximation, and you can do better. I've almost never seen it done in quantum chemistry, but what we did here was we did not put S3 and S4 to 0, but we didn't solve for them. But what we did was we wrote down the equations for S3 and S4, and we kept their self-consistent two-body bits. Do you understand what I say? So it's a way of it's actually better than including S3 and S4 perturbatively. You know, it's not like what doing triples perturbatively. This is doing triples and quadruples better than perturbatively by not putting them equal to 0, but by keeping their self-consistent two-body bit. And that was quite important to get this level of accuracy. Instead of being accurate to 1 decimal point here, it probably without those pieces it would have been 5 or 6 times worse in accuracy. Still good, but not at the level of milli Rydberg. It would have been at the order of 4 or 5 milli Rydbergs.
But one thing that is the how much it is taking the computational cost in terms of if I compare with Monte Carlo, how much time how it is beneficial to
probably a million, maybe 10 to the 8 faster than Monte Carlo. I mean, these calculations were done on a laptop.
Okay.
A 1980 laptop. It probably wasn't a laptop. It was probably a PC. But I mean, they were not difficult calculations.
Okay.
These were, as I said, these were state of the art. I mean, it was the best computer, the biggest computer in the world for weeks at the time.
Okay. Next, that is the for 1D, you have showing the result is accuracy up to the 5 decimal point.
Sorry, please say it again.
In 1D cases, the anharmonic oscillator that is
Oh, this is, yeah.
this is precisely up to 5th decimal. But if you move to second 2-dimensional case, then how much accuracy you are expected in that case?
Yeah, I mean, that's probably probably you're better asking that question on Wednesday,
Okay.
when I will, or Wednesday and Friday, when I'll do, I mean, instead of doing these problems, I'll do spin lattice problems, but lattices of an arbitrary dimensionality. Clearly, as you go up in dimensionality, the computer power gets bigger, but it's offset by the fact that as you go up in dimensionality, you get closer to classical. You know, if you've got an infinite number of dimensions, quantum and classical are the same. So there's kind of an offset there. When you go up in dimensionality, quantum correlations get weaker, but the computing power, if you stick with the same method, gets heavier. But
Okay, thank you.
Sure.
Sir, I just wanted to know, you said that the lack of hermiticity is almost not important.
Yes.
Can you explain further about?
Yeah, I mean, how would lack of hermiticity show up? So what we know is, for example, if we're dealing with self-adjoint self-adjoint operators, which is all physical operators are self-adjoint. Then if we calculate expectation values, or if we calculate we calculate expectation values, they're real. Okay, that's why we deal with Hermitian operators for physical operators. If I were to break hermiticity badly and sandwich even a Hermitian operator between a state and a state that was not its Hermitian counterpart, in principle, I could get complex values coming out. So one sign of the breakdown of hermiticity will be if for example, if I'm calculating the energy and the energy turns out to be complex, then I will know, and that will be an internal sign, right? It will tell, and the only place where that possibly have come from is a breakdown in hermiticity. Do we ever see it in real problems? Almost never. Almost never do we see, and not just for the energy, but for any other physical operator, things like order parameters. They do not become complex, except sometimes exactly at a place where they ought to, which is where you get a phase transition. So sometimes you can even use this lack of hermiticity as to your advantage. Now, just to be, I mean, since you asked the question, does it ever occur? In real many-body problems, it almost, we've never seen it. Electron, gas, nuclear physics, we've never seen this complex eigenvalues. One place where we have seen it is this really tough problem of the anharmonic oscillator. And if you look very carefully at this guy, if you look very carefully in this table, let me come to the bottom of it. These labels A and B, C says the level has an imaginary component. Now, let me find a place where C occurs. We've got one here, right? We've got one here. And this is a value, an enormous value of lambda. This was lambda of 1,000, I think. I think that's the bottom value. What happened? don't think I did that. Do we know how to come? Oh, there we go. Okay. Let's yeah, this is lambda is 1,000. So it's an enormous value. This was the ground state. And you see what's happening with the ground state is even at this very big value of lambda, you're getting convergence to the exact result. But if you look very carefully, there's a kind of not quite a uniform convergence here. Come to the first excited state. The top line is exact. You're getting, you're still getting convergence. You've still got 2 decimal places, maybe 2 decimal places, but it's not quite, uniformly convergent. You come over, but now, you really are pushing it. You're in the 4th excited state. Now the convergence is clearly not great here. It's not great at all. And when I've gone to, and this value, which is somehow it looks, this is exact. This is the first the first place, which is probably n equals 4, because in the lower values you don't get the 4th excited state, so you've got to go to a particular value, and then it starts to converge to this, and then it's dropped below it, and now it's oscillating. And this guy, by the time you've got up here, this guy does have an imaginary component. But you're really, really pushing it into the most wild area. This is a lambda of 1,000 where perturbation theory is, even first order perturbation. It's only first order perturbation theory works. And it's, a million times wrong or something. So sometimes you see it in these really extreme cases. But the equations and we're pushing it, to get the 4th excited state. So you can see it, but in almost all cases of real physical many body systems, and this really is tough because there is no locality in this problem at all. It's 0-dimensional problem, so it's a really tough thing for any many body treatment to do. Does it answer your question?
Yeah. So the couple cluster is basically doing all other perturbation to a quantum many-body system. So, but when you show the example of anharmonic oscillator, you are showing that in the couple cluster method, the energy converges, but in the perturbation method, it doesn't. Yes. But how is that possible? How is that possible?
Well, it's the same story. What perturbation theory is as bad as it gets. It's not only an asymptotic, almost all perturbation series are asymptotic at best. Very, very few perturbation series, they don't really teach you this in undergraduate quantum mechanics. Most series are not convergent. At best, they're asymptotic. And what that means is you've got to do something special to kind of resum them. And there's these things in mathematics that you can do with divergent series are not hopeless. You can resum divergent series, and there's a whole load of tricks to do it, things called Borel resummation and all that sort of stuff. This is about as bad as it gets. This is not only asymptotic, this is really properly divergent. It's got a 0 radius of convergence. So it's as tough as it gets. So nonetheless, to make sense of perturbation theory, you have to do, for almost all examples, you've got to do some sort of resummation. You either do some sort of Padé approximant, which amounts to the same thing, that's a mathematical way of doing these things, or you do one of these Borel resummations. That's typically what people do for this if they're serious mathematicians. Even when you do all of that, you still find the results not that great. Somehow, what the coupled cluster method is doing the proper resummation. And why is it doing it? It's doing it because it's properly counting independent guys. That's the best I can say. That's your gut feeling. And you saw that already at sub 2. You've got this incredible variety of terms that you are summing together in a fully self-consistent fashion, even at the lowest level. So here, you know, when you go, I mean, I know this is nothing like as complicated as a system in 3D from the point of view of diagrammatics, but it's the effect is the same. So what coupled cluster does is a very, very clever, at best, at one level, is a very, very clever resummation of the most important, possibly divergent terms. So, you know, we never do perturbation theory. I stress that again, we don't do perturbation theory, but if I can reinterpret any level of approximation in terms of perturbation theory, as I showed you for that example of S2 where it had all those ring diagrams and ladder diagrams. You could do the same here, I guess. I've never bothered to do it, but you could. And you would find, I'm sure, that you were adding together at virtually every order the most divergent terms in a series that is about as divergent as it can be.
I just wanted to ask, do you have any definition of electron correlation energy rather than saying that is the energy left in the artifact approximation? I would like to know if there is another definition.
No, that is the definition. That's the definition. And so, I mean, what you do is you simply write down the total energy. Suppose you just do perturbation theory for the electron gas, right? You would find you've got in essence, you've got the first order terms, which are the Hartree and the Fock terms, and they're finite. And then if you naively do many-body perturbation theory, what you find, and this is what Bowman pines, that second order theory becomes infinite. It's just because the 1 upon R terms, you know, they're unscreened in the perturbation theory. You know, in physics, the Coulomb is going to get screened, but when you do perturbation theory, that screening's not built in. And so there's a term in second order that blows up, and then every higher order blows up. And what they did was take the most divergent terms from all orders, resum them, and that's what the random phase approximation was. So you do it in essence, if you would start doing perturbation theory, you've got Hartree, Fock from first order, and then what's left over is called the correlation energy. And that's just a definition of correlation energy. So in terms of very explicitly, if you do the ground state energy per particle, you get a term up to a factor. So it's got let's say it's in units. You've got to have a unit in units of the Fermi energy. It's got a term that goes like something upon RS squared, something that goes like 1 upon RS, and then higher order terms. And what's left over, all of this is called the correlation energy. And what was found was that and you would expect this would be, naively, this would just be a power series in 1 upon x. You would expect the next term is a constant, the one after that goes like linear, etc., etc. And what was found was that Instead, this blew up. There was indeed a term that went like RS to the 0, but its coefficient was infinite. And it's infinite in every order of perturbation. There's a term that goes every order in perturbation theory like RS to the 0. They're all infinite, but you add them all up, and magically what happens is that you get a term which goes like the logarithm. And this comes from RPA. Obviously, it's non-analytic in this parameter, and that's the signal of the breakdown of perturbation theory. There's always some non-analyticity turns up, and here it turns up logarithmically. And then there is so this coefficient is known, and then there's higher coefficients, ones that go like RS, log RS, etc., etc. And some higher order ones in this are also known if you're really interested. But
Okay, so let's thank Professor Bishop for this talk, and the next talk will be on Wednesday, right? That's the 22nd, the same time. Okay. All right.